Okay, so the next talk is actually a talk made by Christophe Accadia and Peter Huggard. So we have two speakers. I'm going to give a small introduction to Christophe. Christophe is a physicist by training with a focus on remote sensing and meteorology. Okay, he worked as UK Met Office and in 2005 moved to EUMETSAT.
Yes.
And so today he's going to speak about EUMETSAT Polar System second generation. And I'm going to introduce Peter as well. Okay, so and Peter is one of our local champions. Okay, so Peter leads the millimeter wave technology program at RAL. He's developing and delivering state-of-the-art technology for Earth observations, radio astronomy, and atmospheric science. Okay, thank you.
Thank you. So, first of all, thank you for inviting me, because it's a pleasure to be here. It's quite interesting. I feel humbled after seeing what I've seen so far this morning and even now. So my pleasure now is to give you just an overview of the EUMETSAT Polar System second generation satellites with some highlights and let's say on my preferred sensors, the microwave sensors. So let's start. So first of all, EUMETSAT EPS-SG's socioeconomic benefits. So why we do this? The EUMETSAT Polar System second generation is a key asset. It's let's say the full-on system of the system that actually is in orbit now in low Earth orbit, is providing continuity and expanding also the capabilities. So there are many applications that we have impact on. Like, of course, NWP, numerical weather prediction, could be space weather in future, and also climate monitoring, surface monitoring, and so on, ocean hydrology, and land surface. So observations are, of course, very important for supporting many applications, economic resilience, and climate change adaptation, which is nowadays quite important. One analysis made some time ago was mentioning that the expected, let's say, socioeconomic return is around 20-1 in terms of investment of our member states. So this is quite, and this is quite a conservative assessment. So, METOP SGA1 status at the moment. So we launched successfully on Ariane 6.2 on 13th of August. It went in orbit. Unfortunately, this will be one of the satellites that will a bit disturb the Vera Rubin telescope, but we try to do our best to minimize. And of course, is providing many observations during the day, 14 orbits, 831 kilometers altitude, local time of the ascending node 21:30. So maybe yes. But we had a flawless launch, flawless early orbit phase, and we got to the satellite by mid-August. We started all the activities, and the in-orbit validation was completed on 13th of November. Now we are in what we call in our sector the CalVal phase, calibration and validation phase. So we are assessing how the instruments behave, how they are stable, what needs to be tuned, and so on. So here it is. This is the satellite, 4.4 tons, if I recall correctly. It's like a bus going 27,000 kilometers an hour in orbit. It's quite impressive. There are several instruments. I cannot show you all today because it's quite, there are many. But there is infrared atmospheric sounding on board, IASIN Nouvelle Génération, it's French, or New Generation. The microwave sounding mission, which I will show you in a moment. MET-IMAGE, which is a visible infrared imager at a high resolution, covering many applications. radio occultation, which I will also explain briefly, and what we call the 3MI, the multi-viewing, multi-channel, multi-polarization imaging spectrometer. Then we have a Copernicus Sentinel-5 that has been tested here in the facilities at RAL, which is providing UV, visible, near-infrared, and shortwave infrared sounding capabilities. It's a Copernicus mission. So, radio occultation, what is it? It's, let's say, exploiting the capability of having many GNSS sources in the sky. And what you see here is that each one of these points was a successful tracking of a GNSS signal through the atmosphere. And through this signal, the atmosphere is changing let's say, the electromagnetic behavior of the signal. And this allows you to get information on temperature, humidity, pressure, and also if you are tracking a very high altitudes, also on the total electron content, which is linked to space weather. So you can actually observe the GNSS systems and get information on the state of the atmosphere and provide this information near real time to the NWP users, which are using this measurement as a foundation measurement, because it's a measurement that is only based on time. So it means that you don't need calibration, you need just very precise clocks. And I have to say the amount of precision, it's amazing. We are at the level of nanoseconds in order to get the position of the satellites right, and also the speeds. It's like a ballet between two satellites, but at the end of the ballet, which lasts about 1 or 2 minutes each time that there is a link, you are able to get an information about the state of the atmosphere with a vertical resolution that is quite impressive. And this is quite amazing, I would say. What you can also notice over, unfortunately, Ukraine, is the area where military spoofing is active. And this is actually a problem because it's impacting the number of occultations. So in some cases, you have this kind of issues. Sometimes it happens also in the region of Taiwan. We have seen this as well, unfortunately. But it's an issue. This is a team effort. The radio occultation sensor has been designed by Beyond Gravity in Sweden under an ESA contract. So let's go on. So this is the first orbit of the microwave sounder data. This is already quite an achievement because it was about 10 days after the satellite was in orbit. We did switch on the instrument, it started to spin, it was happy. And then we got the first measurements. This was the first orbit. What you see here is 31 gigahertz channel. I will show you the rest, but just to give you an idea why microwave sensing is important. You can see at night, it's very useful. So is able to be on all-weather measurements because of the wavelength can penetrate in cloudy regions and provide information where there is the weather actually. So you can actually observe clouds, precipitation, provide information on temperature, humidity, and so on. So it's quite a powerful technique. Let's go on. Actually, I go back because I just wanted to give an acknowledgement to RAL because he contributed to some of the components for the microwave sounder. So I think it's an important element to recall here as part of the industrial team led by Airbus that built the MWS. So this is just to give you an idea. This is 1 day at another frequency, but it's the same planet, but different time, slightly different. So this is 89 gigahertz, is what we call a window channel. You can see why, because you are able to see both the ocean and the atmosphere at the same time. And also, if you pay attention, I will try this is wrong button. Okay, I go back. Okay, pointer. You see, okay, you see, let's say west of the Europe, you see a nice storm brewing already there. So this is, let's say, it can provide information, for example, on sea ice, on many other observables. This is just to give you an idea. This is what we call the stamp plot, for obvious reasons, but it's also because it gives you an idea of the amount of information that you start to get from such a sensor, because there are some channels in the upper left that observe very much the surface, but can provide information, for example, on water vapor, humidity, sea ice. You start with in the middle, you have the channels that are sensitive to temperature, so you get an information on the temperature profile in a all-weather, with an all-weather, all-time, night and day capability. Then you start to go through the water vapor channels, and this is where you have information on water vapor, of course. But you can also extract information on rain rate, ice water path, and other observables. Then we have the very last channel at 229 gigahertz, very high frequency so far. And this is a channel that is very useful to observe cirrus clouds. So in this way, you can detect where profiles are affected by cirrus clouds or not. And this actually is relevant when the numerical weather prediction people is assimilating this kind of information in order to characterize what is a cloud and what is not, and making a better use of these soundings. So this is not theory, this is recent. This is the storm Amy that was striking UK 2 months ago. And this is, let's say, showing the structure of the cyclone at the various channels. There is a huge amount of information here. I'm not dwelling on this because there is a lot to say, but for example, at low frequency, you start to see the emission signals, so the warmer regions in brightness temperature due to the precipitation. At high frequencies, you start to see the diffusion, the scattering of ice particles, and so this reduces the temperature, the brightness temperature that you see, and so you see the structure of the front. Just to bring you there, this is the Met Office UK Met Office analysis for that day, and I did put the 183 plus minus 7 gigahertz channel together, and you see how respondent is at least to the ground analysis that was made on that day. This kind of data is useful, is helping to save lives, to protect property, is fundamental, and EUMETSAT is delivering this kind of data 24/7 every day, every year. So 3MI, nice plots here. This is I'm out of my turf, but I will try to honor the work of my colleagues, because this is actually a set of images just with the satellite moving. You have to imagine the sensor is underneath and is just moving over the Earth. And this instrument has the capability to observe the Earth at multiple angles, multiple polarizations. What does it mean? It means that you can observe particles of aerosols and characterize the aerosol precisely. In case you have an event like the Icelandic volcano, that I will try to repeat, is Eyjafjallajökull, but forgive me if my pronunciation was not correct. One of these instruments will help to characterize where you have volcanic ash, where you can divert the traffic from commercial aviation and so on in real time or quasi real time, depending where you are, or providing support to the Met offices in order to derive this information. As you are seeing, this is an instrument designed by Leonardo in Italy. In general, as everybody was saying here, space is a team effort. So I need to be very fast. So this is the future, just a glimpse. This is the next satellite that we will launch next year, summer 26. There is MWI, the microwave imager, and ICI, the ice cloud imager. This is a brand new satellite, a brand new set of instruments, because actually they have new capabilities. At least this is the first operational imager made in Europe, while the ice cloud imager is a completely new mission dedicated to ice clouds going to the sub-millimeter range. And this is also where RAL did contribute. I think Peter will provide a nice overview. Just to give you an idea, let's see if I can do this. This is a bit what I was showing. Look at the blue line on the right. This is the microwave spectrum, and on the left. And then on the right, you see the associated image. You start to see the impact of clouds, how the atmosphere changes at the various channels. And you see the amount of information that you can get from this. This is from the MWI, the microwave imager, but we go to the ICI. So you go up in terms of frequencies, and ICI is, let's see if I can show you. This is, this is sorry, this is still the MWI. Let's go to ICI, and then that's it. So ICI is the new kid on the block in terms of space observing systems, because there is no observing system that is going to frequencies higher up as 664 gigahertz. So this is quite a novelty. And it's meant to be the ice cloud mission. Its main objective is to observe ice clouds, and because these are actually one of the least understood systems at geophysical level to characterize the climate impact. And so this is the response of the community to a question that where the answer so far is we don't know that well, and maybe this mission will help us. To shed some light. So I think I can conclude, let's see, with a big thank you for your attention, and also thank you for having me here. Thanks a lot.
Good afternoon. Thank you for the invitation. It's an honor to be here because I'm just a spokesman for the sweat, the weekends, the evenings of many people in the department getting the equipment ready for space that delivered those magnificent results that we've just seen from Christophe. So I'll talk very briefly about some of our contributions to METOP second generation, the development of these ultra-sensitive radios that detect the millimeter waves, building the pre-launch calibration apparatus for one of the instruments, the microwave sounder, the calibration of another instrument, very briefly, and what we're going to do with the data. Christophe has shown the instruments. Satellite A is in orbit since last August. We calibrated Copernicus Sentinel-5. We will take some data from IASI, the infrared atmospheric sounding interferometer next generation, and the microwave sounder is something I know intimately. And the next satellite B, Christophe has just presented the two conical scanning instruments, thingy bulbs, microwave sounder and ice cloud imager. So how does this thing work? Oh, it does be really slow. So the MWS here at the arrow is actually a cross-track scanner, so it's got a rotating mirror in here. We'll see this later on in my talk. This is what the atmosphere looks like. As Christophe has said, there are many channels. Due to quantized quantum mechanics, we have absorptions from oxygen molecules, water vapor. The atmosphere is not uniform, and these lines, the strength of them depends on the local temperature and pressure. And so by measuring the spectrum using these radios, we can get information that's a vital input for numerical weather prediction and climate conditions. And the advantage of millimeter wave, it works 24/7, light and day, and clear and cloudy conditions. And there's various channels. The ice cloud imager information is on the right. That will have the unique channel of 664 gigahertz. We built some years ago an instrument called ISMAR for the UK Met Office, which is sort of a groundbreaker for this. The one instrument I know best is called Microwave Sounder. It was produced by Airbus Defence and Space in Portsmouth. They gave me this image, all credit to them. This is the outside of the image. They wouldn't show me the inside, but we've got the scanning mirror here. It looks at an onboard calibration target here. And what's inside is a quasi-optical network produced by the SME Thomas Keating Limited. So we have a mirror that takes the radiation from the molecules, sends it into this network of mirrors and dichroic filters, frequency selective surfaces, that direct the radiation to a number of ultrasensitive receivers. So it goes from free space into these things called feed horns, and we bolt our receivers on the waveguide output there. There's a set of receivers in there covering between 23 and 229 gigahertz. This probably does the slides too. So our contribution, we led a 20 million whatever euros, pounds value project in collaboration with radiometer physics in Germany to supply front-end receivers for METOP, second generation. There were 5 sets of receivers for MWS covering 3 different channels, MWI 2 channels, and Ice Cloud Imager 5 channels, highest frequency, unique 664 gigahertz. The work share, the radio frequency modules were done in collaboration with radiometer physics. RAL staff did the DC electronics, and the assembly of receivers was shared with radiometer physics. They did ICI, and we did MWI and MWS. At the bottom is a typical receiver, one of the channels. So the signal comes from space, goes through the quasi-optic network, enters the feed horn, and then it goes into a waveguide, and then is coupled into a low noise amplifier. So I'll describe the packaging of this. The amplified signal goes to a mixer where it's down converted from, say, 200 gigahertz to roughly 10 gigahertz, where conventional electronics works. And to pump this mixer, we need a local oscillator signal. So we take 2 oscillators. These are frequency tripled, amplified, and then passed to the local oscillator. And all this technology of tripling and mixing is based on Schottky diodes, which come from our spin-off company, Teratuck Components. As I say, other suppliers are available. So the typical receiver is a unit about 20 centimeters high, and it's composed of a stack of modules, each of which performs a different function. So an individual module might be a low noise amplifier down here on the bottom. The radiation enters a waveguide, which is about, say, 2 millimeters by 1 millimeter in the center of the flange. And if we split that block open on the symmetry plane, the waveguide is this kind of, sorry, I need a steady hand, this structure here, this curving structure. So the radiation comes in the waveguide and then passes through a precision engineered coupling structure into a low noise amplifier. This is a magnificent achievement by Fraunhofer Institute in Germany. These achieve state-of-the-art amplification and low noise. We spent a lot of time getting these to perform at their optimum, designing these transitions from waveguide, biasing the individual transistors. This is, by modern integrated circuit standards, this is a very simple circuit. It's only got half a dozen transistors, but nevertheless, these are challenging. They're challenging to make and to get to work with this level of performance. So, having built one of these things, we then are able to test it and check what it's like. And this is measurements in the intermediate frequency from 0.5 to 8.5 gigahertz. We see that Our performance is very flat. Our noise figure is 5 dBs, or in temperature for those microwave people about 630 Kelvin. We're comfortably below the forbidden zone, the performance limit, and the overall gain is at the bottom here is between 47 and 50 dBs. We have 2 DROs in there, so no matter which one we use, we get more or less identical performance. And this is why the instrument is so good, because we have such excellent performance. Having made these receivers from Metop second generation, we've then been able to adapt them and sell them to the company Spire Global. And so the next set of receivers on their satellite are due for launch on January the 5th. Having supplied your receivers, they go to Airbus, the quasi-optical network comes in, the whole thing is assembled. We then need to calibrate this before we launch it. Calibration is critical for radiometers. And this shows the radiometric calibration test rig produced under contract for Airbus for MWS. MWS sits here at the back. These large things are calibration targets, black body calibration targets at the bottom of temperature shields. These are almost perfect absorbers, which means they're almost perfect emitters. So if you know their temperature, you know how much radiation they're emitting, and therefore you're able to calibrate your receiver. These are of an unprecedented size. These took us a lot of effort to get to making this size. And we put strenuous thermal engineering into these to ensure that we would have temperature uniformity and temperature stability at the level of 1/10 of a Kelvin. One of them represents the view into cold space, and it's cooled to 85 Kelvin. It doesn't move around. The other one represents the Earth view. It's variable in temperature, between 85 and 335 Kelvin, a bit over room temperature. And because the instrument itself scans through a big arc across the surface of the Earth, we have to be able to move the target. And you can just see the wheels here, so the whole calibration target moves around a circular track. Inside those large silvery pots is a spiky calibration target. We have a small one at the back of the hall. We also have some receivers that you can see. Look through the microscope to see the beauty and the perfection of all the engineering. This target has got precision machined aluminium spikes coated with exactly 1.4 millimeters of epoxy, iron-loaded epoxy, which absorbs the microwaves. And as I say, it's an almost perfect reflector. 1 part in 30,000 of the incident microwaves is reflected. This plot here shows the different channels of MWS, and that the curvy line is the data, and it shows that over nearly the whole operating range, we achieve the required reflectivity performance. Having got your target, that's only part of the battle. You've got to control its temperature. And we do this in a couple of ways. One, by putting it in a pot so that it restricts the field of view. And second of all, by controlling the temperature of the walls of that pot, because they're emitting radiation and absorbing room temperature radiation. So we want everything inside the pot or baffle to be at the same temperature as the target. So we do this by surrounding everything with a liquid nitrogen jacket. And then between that and the target, we have a gas gap that we can fill with helium gas under low pressure. So this is a variable, if you like, variable temperature leak. But we want the target cold, we put a high pressure of helium. We want the target warm, we evacuate the helium and use some foil heaters around the periphery to, in a strategic manner, to up the temperature of the whole assembly. The back of the target here, back of the spiky area back of these spikes here is peppered with temperature sensors, and we have a calibrated from NPL platinum resistance thermometer right in the center. Moving now to the shorter wavelengths. This is an example of Copernicus Sentinel-5, one of the instruments outside our 5-meter vacuum tank. We had a contract from Airbus again to calibrate to, characterization and calibration for this. Because it's a UV instrument, keeping the optics clean is critical, so you'll see the people in the clean room staff are fully suited. We had to build mechanical ground support equipment. This positioned a target in front of the instrument, a calibration target, and also move the instrument about 2 degrees of freedom. This is a photo taken during one of the campaigns. The Sentinel-5 that's in space was calibrated in May 2024. We have a model either just in the chamber or just finished testing, and next year we'll get the 3rd model. Finally, move on a bit to the data. We have a remote sensing program in the department led by Brian Kerridge. For many years, they've been working on infrared microwave sounding schemes funded by NERC's National Centre for Earth Observation. This has been working on existing space data from METOP and Suomi. And from this data on the instruments on board, they get retrievals about temperature, water, ozone, and various other gases related to human activities of climate change, as well as methane. There's a link there, hyperlink there, where you can look at their site. And this infrared and microwave sounding scheme will be adapted to use METOP data from IASI and MWS. And our influence also goes beyond the data because we have staff member Richard Siddons on the mission advisory groups for Sentinel-4 and Sentinel-5. And just to show you an example of what this group does, this is the release of methane following an explosion caused by humans on the pipeline in the Baltic. 200 kilotons of methane were released, a tenth of the global daily leak. The plot here shows 7 microns data. This is the initial release just off Denmark. Then there were 2 cloudy days. Unlike microwaves, the infrared doesn't see through clouds. And then later on, we can see the plume. It forms a crescent shape off the coast of Norway. And RAL data was then supplied to the University of Leeds, who put a model. And I don't know if this will work or not. Yes, it does for once. It shows the plume evolving and forming that kind of crescent shape off the Norwegian coast. So that's really a summary. As I said, I'm just a spokesman for people who worked really hard to get this right, and it's a great pleasure to see it in space and working now. Thank you very much.
Thank you, Peter and Christophe. Any questions for our 2 speakers about EUMETSAT? No? Online, maybe? Okay, we do have one over there. Yeah.
Oh, thank you. Hi, Liz Quintana from Ofcom. Thank you so much for such a wonderful presentation, fantastic engineering, and you're going to have to come and give that presentation again. That'll make our engineers really, really, really happy. So my question is, as you might imagine, about interference, and you're operating across several different bands, and there are some of those bands, you're the only ones there, and that's wonderful, and there's a lot going on nationally and internationally to protect those frequencies. There are others starting to operate in and around some of the other bands, and so I'm just curious what mitigation measures you have in place, if there's software that you can use to help, and obviously it's not just about other users. You were saying there was temperature and other things that might affect the frequencies that you measure in, but yeah, be really interested to hear a bit more about that.
It's an interesting question, and it's ongoing, let's say, work in order to ensure that the bands are protected. What we are talking here is about radio frequency interference, which is quite a relevant issue for us and for many others. In general, we are, at least at EUMETSAT, is quite active in terms of ensuring that ITU regulations protect all the bands that are relevant for remote sensing in the microwave domain, or in the sub-millimeter domain, as we enter now in the next year. Because actually one of the steps that was made was to protect the 243 gigahertz band, for example, which is a new channel. And just because now we will have the ice cloud imager with that frequency range. However, it's quite a continuous activity, because you cannot lower the guard with respect to the protection of the relevant bands. There are some other missions in the future where this task will become more challenging. For example, I'm talking about the Copernicus imaging microwave radiometer. This goes from L band, so 1.4 gigahertz, to Ka band, 36.5 gigahertz. And in that case, it will be a continuous work to ensure that the regulations are followed, especially for L band, which is also shared. We are very thankful to astronomy in this case, because the L band is useful for astronomy in order to track hydrogen in the galaxies, but is also very useful to track soil moisture on Earth. And for us to have a clean L band has been quite a long effort. For example, ESA with the SMOS mission has been pushing a lot on the regulatory side in order to make sure that L band is clean enough. The other element is, of course, that maybe in future we have to design instruments in order to be capable to cope with a, let's say, RFI environment that is becoming more and more difficult.
Could I just comment on that?
Yeah.
We are doing things like a hyperspectral microwave sounder, where we have, instead of the more conventional coarse spectroscopy, we have higher resolution digital sampling, and so we are able to filter and reject the channels contaminated by human activity. But prevention is better than cure, right? Yeah.
Thank you very much again for our two speakers, and we need to move on to the next. Thank you.